Welcome back to biology, everyone. So I made this video for you all, and then I became aware that there was no sound on the video. So this is another attempt to make this video for you so that we can talk about simple diffusion. Simple diffusion is the simplest way for something to get into a cell or out of a cell or to cross a cell membrane. And it is just some simple little molecules go straight through that membrane. It doesn't have to have anything help it. It doesn't take any energy. It's just small little things move straight through that membrane. Really only small things like oxygen and carbon dioxide, gases like that. Nonpolar molecules, so that could include like even hormones like estrogen or benzene could do it. And very small polar molecules. So water, ethanol can go through that plasma membrane. And it is always going to be moving towards equilibrium. So here there's a lot of this molecule outside, so it's going to move towards the cell, into the cell. Just like if you're on an elevator, as people get on the elevator, you spread out. These molecules are doing the same thing. They're going to spread out. They say there's lots of room on that side of the elevator, so some of y'all move over there. If there were a lot of these molecules here, simple diffusion would have them move across to the other side. One example we can see is oxygen and carbon dioxide in our erythrocytes. So your erythrocytes are your red blood cells are responsible for carrying oxygen and carbon dioxide around your body. So in your body tissues, where your body, as soon as they get oxygen, they're using it up. So there's a low concentration of oxygen. As they're going through metabolism, using sugar for energy, they're going to be producing carbon dioxide. So there's a high concentration of carbon dioxide. As your red blood cell comes there, the red blood cell is going to pick up carbon dioxide because there's a lot of carbon dioxide outside, not a lot inside. It's going to let go of its oxygen because it's carrying lots of oxygen. There's not a lot of oxygen there. It's going to diffuse outside. Simple diffusion, completely based on concentrations. Carbon dioxide moves into the red blood cell and oxygen moves out in your body tissue. So now your body tissues have oxygen. Now your red blood cell has all this carbon dioxide. It travels back up to the capillaries of the lungs. And in the lungs, you've just taken a nice deep breath. So you have lots of oxygen here. And you have low carbon dioxide because you're breathing all of that out as soon as you make it. So in your lungs, carbon dioxide is going to release from your red blood cell. It's been carrying it up here from your body tissues. Now it's going to release in your lungs and diffuse out. Just naturally straight through there just because of concentration. And then you breathe out that concentration. The oxygen that's really high in your lungs is going to diffuse in. Your red blood cell doesn't have any oxygen left in it. So now it pulls in this oxygen. Now it has oxygen. It can go back to your body tissues, deliver oxygen to your body, pick up carbon dioxide, come back to your lungs, drop off carbon dioxide, pick up oxygen. Circulating through your blood, making sure all of your body gets oxygen just through simple diffusion based on just that simple concentration gradient inside and outside of the cell. So chemical reactions and physical processes both, they're going to proceed in the direction of decreasing free energy. So if I'm at the top of a diving board, I have a lot of potential energy. If I jump off of that diving board, I'm going to go down into the pool. That is where I have less free energy. If I'm a ball at the top of the hill, I'm going to roll down the hill because that's where I have less free energy. So this is just diffusion doing the same thing that all chemical and physical laws require, decreasing free energy. It's moving down its concentration gradient, spreading out. Just like if you spilled some water on a table, it's going to spread out. Just like anything is going to move towards free energy, towards decreasing free energy. Eventually, these molecules are going to come to a point of equilibrium where you have a balance between what's inside the cell and what's outside the cell. And at that time, you have no net movement. That means some movement might still happen out, but it'll be balanced by things coming back in. And some things are still able to come back in, but that'll be balanced by going out. But at that concentration equilibrium of this purple molecule, what moves in is balanced by what moves out. So there's no net movement. Overall, it stays balanced. One specific type of diffusion is osmosis, and osmosis is the diffusion of a water molecule. So what we were just talking about here, if you have this tube and you put this fake cell membrane in here, so it's going to act just like any other cell membrane. If you put a lot of solute on this side, so a lot of sugar, a lot of salt, a lot of whatever, and a little bit on this side, if that solute can go through the membrane, it's going to move through the membrane until it comes to an equilibrium. However, if this membrane is impermeable to the solute can't pass through it, the cell still wants to reduce its free energy. It still wants to even out and come to an equilibrium. And the way it's going to do that is by moving the water. So you can't move the salt, so you move the water. So the water over here moves over here. And now you can see you've got a balance of the concentration. It's about the same on both sides of this membrane. Because the water moved, you can see now you have more water on this side. Eventually, so much water is going to start to push back and kind of cause some pressure there. But you've moved your water to come to a concentration equilibrium. That's what osmosis is. Water molecules are uncharged, so you don't have to worry about what kind of charge dynamics are going around across the membrane. So water is going to stay pretty consistent inside and out of the cell. If you increase the concentration of solutes outside of your cell, the water in your cell is going to move out. If you decrease the concentration of solutes inside of the cell, the water in the cell is going to move, the water from outside is going to move into the cell. So that osmotic movement, that movement of water moving in and out of the cell, is related to osmolarity. Osmolarity is telling you how much concentration of stuff is inside the cell and outside the cell. Some concentrations are hypertonic. So think of like a hyperactive kid. They're extra too much activity. A hypertonic solution has extra too much stuff. So here you have all of these green solutes out here, not as much as what's here. So what's going to happen to that cell? If the green stuff can't diffuse to come to an equilibrium, how are you going to get an equilibrium here? The water is going to have to move. And which way is the water going to move? The water is going to move out of the cell to here. So the water is going to try to dilute all of this solute out here. That means your cell is kind of going to shrink up. If, however, your cell is in like pure water or water with very hypo, so hypo means low, how is the water going to move there? So here, there's less solute here. For the water to balance out, water is going to move into the cell. So if that water is moving into the cell, that means that cell is going to start to swell. And if nothing can control that swelling, eventually that cell will burst. And then here's an isotonic solution. So iso means balanced, kind of. So you have an equal level of salt or sugar, your solute concentration on either side of the membrane. So some stuff can come in and it'll be balanced by what's going out. So you're going to have a pretty balanced flow of water in and out. That cell is going to stay about the same size. So if you're looking at your red blood cells, cells will shrink or swell as you change the concentration gradient of what's outside of them. So if you are a nurse, or if you're a patient even, the nurse comes and gives you an IV. You want that IV to be isotonic so that when it hits your red blood cells, when it's in your blood, your red blood cells can be nice and healthy and keep functioning. If you are given a hypotonic solution, so you give your patient pure water, no saline, just pure water in their IV, that's a hypotonic solution. It's going to cause water to start filling into the cells. You can see these red blood cells are getting really filled, and this one's even bursting to the point where you have just really harmed severely your patient. If you give your patient a solution that has too much salt and too much sugar and too much solutes in it, when it hits their blood, the water is going to move out of their cell to try to dilute that solution around it, and the cells are going to shrink. And these will also not be very functional red blood cells. They won't be able to get the oxygen to their body or to their brain, and that is also going to be very severely dangerous. If you're a cell with a cell wall, that cell wall creates something called turgor pressure. So if you're filling up a water balloon and you just put that water balloon on the sink and let the sink keep dripping into it, eventually it's going to overfill and burst. But if that water balloon is inside of a box that presses against that water balloon, the water balloon will fill until it's the size of that box, and then the water will start being pushed back out. That's what your cell wall is doing in a plant or a fungus or an algae or something. That cell wall is pushing out extra water. So if they're in a hypotonic solution, as water comes in, it'll fill up their vacuole. They'll be nice and healthy. But that turgor pressure that is created by their cell wall will push extra water out. So their cell is less likely to burst here. In a hypertonic solution, water is still going to be drawn out of the cell into the solution around it. And that means that their cell is still going to shrink. That plasma membrane is going to shrink down. But because that cell wall is rigid, it's not really going to move much. So that plasma membrane is going to pull away from the cell wall to shrink down into here. You can see instead of being nicely attached, it's all pulled in here. And that's called plasmolysis. To deal with osmolarity problems, our cells, which do not have a cell wall, will pump out inorganic ions to help make your solution less hypotonic, to help this hypotonic solution become more isotonic, to minimize that osmolarity difference between the cell and its surroundings. Okay, so what else can affect how things are moving through the membrane? One of those things is the size of the solute. So lipid bilayers tend to be more permeable to small things like water, oxygen, carbon dioxide. Typically things that have a molecular weight smaller than 100 Daltons. If it's smaller than 100 Daltons, it can probably diffuse through the membrane through simple diffusion. So something like ethanol, which has a molecular weight of 46, and glycerol, which has a molecular weight of 92. By the way, I'm not going to ask you to tell me these numbers, but they're small, so you know they can diffuse right through the membrane. In contrast, glucose has a molecular weight of 180. That's a lot bigger, so it cannot diffuse through the membrane. It is going to require some kind of protein to make a channel or a tunnel that it can go through. However, even though these small things can go through the membrane, if you add a transport protein to it, it'll move a lot faster. So just waiting for it to go through the membrane, it'll happen eventually, but if you want it fast, that cell will make a transporter to get those things in and out of the cell. The polarity of the solute also makes a difference because we have this hydrophobic core here. Things that are hydrophobic or nonpolar are also going to transfer through that membrane a lot more easily. So here you can see this molecule like benzene. It is nonpolar and it can travel right through that membrane. It doesn't have a problem interacting with these lipid tails. Something like estrogen or testosterone, even though they're getting rather large, they still go through that cell membrane because they are nonpolar. You can measure how polar something is by measuring its partition coefficient. And in that, you're going to see in this tube, I have some water, which is pretty hydrophilic, and some ether, some organic solvent there that is hydrophobic. And then I add my molecule. So here's my red molecule. And I can see my red molecule, a lot of it is dissolving in this top part and a little bit of it in this bottom part. And I make that ratio of what's at the top compared to what's at the bottom. And I can see how hydrophobic something is. So if something is really hydrophobic, it's going to stay at this top part more, have a higher coefficient. If something's really hydrophilic, it's going to move into the bottom part more, which means it'll have a lower partition coefficient. Solute charge also makes an impact on being able to pass through that membrane. And one of the reasons why is because a lot of ions will form a hydration sphere around them, or a shell of hydration. So here this chloride ion, has a negative charge. So all the water molecules in solution are going to orient themselves around this ion, where the positive, that's what this delta plus means, the positive ends of these hydrogens are going to interact with that ion. Here, sodium, which has a positive charge as an ion, the oxygen end of the water is going to orient themselves, and they're going to be attracted to that water molecule because the negative and positive charges attract, or the positive and negative charges attract. So if you're going to get that through that membrane, because all this water just makes it turn into a big old thing, to get it through the membrane, you would have to take all this water off it to make it small, and that's going to take more energy than the cell is willing to give to it. So ions, that is another reason why ions don't go through the cell membrane. Okay, I hope that you have a better understanding of simple diffusion. We still have some videos to talk about facilitated diffusion through a transport protein, and active diffusion, or active transport, which is going to use energy to get through that molecule, through that cell membrane. Okay, see you later. Bye.